In episode 88, titled Data Exfiltration, Paths, Choke Points, and Practical Controls, the focus is on a simple but uncomfortable reality. Most exfiltration happens through pathways that are allowed to exist for legitimate business use. Attackers rarely need a magical backdoor when they can ride normal outbound connectivity, blend into routine protocols, and take advantage of permissive egress rules. That is why exfiltration is less about stopping all outbound traffic and more about shaping outbound traffic so sensitive data has fewer escape routes and more observable choke points. The exam framing tends to reward practical control thinking, where you can describe how data leaves, where you can watch it, and how you can slow or prevent it without breaking the business. Before we continue, a quick note. This audio course is a companion to the CloudNet X books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Common exfiltration paths usually mirror the common ways systems communicate outward, which is why defenders must understand normal outbound behavior before they can spot abuse. Web traffic is the most common path because Hypertext Transfer Protocol Secure is widely permitted and can carry almost anything inside encrypted sessions. Domain name system tunneling is another path because domain name system queries are often allowed broadly and can be abused to smuggle data in small chunks through query names or responses. Cloud storage services are attractive because they are legitimate, high bandwidth, and widely used, and they can look like routine file synchronization when a compromised host begins uploading. Email remains a persistent path because it is built to move information outside the organization, and compromised accounts or automated clients can leak data in attachments or message bodies with alarming ease. The important point is that the paths are ordinary, so the defense must focus on control points and policy rather than assuming the path itself is inherently suspicious. Identifying choke points is how you turn a messy outbound landscape into something you can monitor and control, because choke points are places where traffic converges and visibility is feasible. A choke point might be an internet egress gateway, a proxy tier, a network firewall, a secure web gateway, or a cloud egress control service that all outbound traffic must traverse. The value of a choke point is that it reduces the number of places you need to instrument, the number of policy engines you need to manage, and the number of telemetry sources you need to correlate. In hybrid networks, choke points also help unify on-premises and cloud egress, so outbound controls do not become inconsistent across environments. When choke points are designed intentionally, defenders can enforce policy, log behavior, and create reliable detection signals without attempting to inspect every endpoint individually. Egress controls are the practical heart of exfiltration defense because they define what is allowed to leave, where it can go, and under what conditions. Allow lists are powerful because they invert the usual model, where everything outbound is allowed unless blocked, and instead require destinations to be explicitly approved. Proxies add control because they can enforce policy at the application layer, authenticate outbound sessions, and generate rich logs that make investigations possible. Restricted destinations can be expressed in many ways, such as blocking unknown cloud storage domains, preventing direct outbound traffic to the internet from sensitive segments, or forcing all outbound to traverse a controlled gateway. The exam typically expects you to recognize that egress control is a preventative measure that reduces the attacker's options, which is often more reliable than trying to detect every leak after it starts. A useful way to think about egress controls is that they create friction and reduce anonymity, both of which are bad for attackers and good for defenders. When outbound access requires a proxy, the actor is more likely to be identified because sessions can be tied to devices, identities, and policy decisions rather than to raw Internet protocol addresses alone. When destinations are restricted, attackers are forced to use fewer paths, which increases the chance their activity will stand out against baseline behavior and will hit known monitoring points. When outbound traffic is segmented by sensitivity, a compromised host in a sensitive zone has fewer allowed channels to the outside world, which buys time for detection and response. Friction is not about making systems unusable, but about making abuse harder than normal work, and that is a reasonable security design goal. In practice, well-designed egress controls reduce both the frequency and the severity of successful exfiltration events. Data loss prevention, often called DLP after first mention, plays a specific role in this picture by focusing on content awareness and policy enforcement when sensitive patterns appear. Data loss prevention systems detect sensitive patterns such as regulated identifiers, confidential document fingerprints, or classification labels, and then enforce policy by alerting, blocking, quarantining, or requiring additional authorization. The exam framing often treats data loss prevention as a detective and preventative layer, depending on whether the policy action is monitor-only or actively enforcing. The strength of data loss prevention is that it can catch leaks that do not look unusual at the network level, such as a user emailing a spreadsheet externally or a script uploading a file that appears normal in size and timing. The limitation is that data loss prevention is only as good as its policy coverage and its ability to inspect relevant channels, which is why it must be paired with choke points and egress shaping. When you view data loss prevention as one layer, not the only layer, it becomes a practical tool rather than a false promise. To ground this, consider a scenario where a compromised host begins uploading sensitive data to an external service that is legitimate and widely used, which makes it difficult to spot by destination alone. The host might package data into archives and send it over Hypertext Transfer Protocol secure, blending into routine web traffic, or it might use a cloud storage application programming interface, often shortened to API after first mention, that looks like standard synchronization. If outbound access is broad, the upload succeeds quickly, and the first sign might be after-the-fact discovery through logs or an external notification, which is the worst time to learn your controls were too permissive. If choke points exist, the upload can be observed, and if egress policy restricts unknown destinations, the attacker may be forced into a narrower set of options that are easier to detect. If data loss prevention is applied at the right layer, sensitive content can trigger enforcement even when the destination looks harmless. The scenario shows that the best defense is not one tool, but a coordinated set of constraints that slow the attacker and amplify visibility. The first pitfall is allowing broad outbound traffic and relying on detection only, because detection without constraint often becomes an exercise in watching data leave in real time. Broad egress gives attackers unlimited destinations and protocols, which means they can select paths that avoid your best monitoring and can shift quickly when blocked. Detection-only approaches also tend to produce alert fatigue because the volume of outbound activity in modern environments is high, and defenders can drown in noise while the real leak hides among normal traffic. Even strong analytics struggle when the allowed space is huge because anomalous becomes subjective and attackers can mimic normal behavior by exfiltrating slowly or during peak hours. The exam frequently pushes you toward the principle that prevention and restriction reduce the problem space, making detection more reliable and response faster. Broad outbound access is convenient, but it is a convenience that often trades directly against control and visibility. The second pitfall is assuming encryption makes the problem go away, or assuming encryption makes the problem impossible, because both conclusions are overly simplistic. Encrypted channels hide content from casual inspection, which means you cannot rely solely on content-based detection if you cannot inspect the payload where it matters. At the same time, encryption does not hide everything, because metadata such as destination, timing, volume, and protocol behavior can still provide strong signals, especially when compared to baselines. Proper controls for encrypted channels often involve proxying with inspection in approved contexts, enforcing certificate validation, restricting direct outbound, and using application-aware logging that captures meaningful context without needing to see every byte. The exam tends to reward the idea that encryption changes what you can observe, not whether you can observe at all, and that you must design controls accordingly. When you treat encryption as a design constraint rather than an excuse, you build defenses that remain effective even when content is opaque. A quick win that consistently reduces exfiltration risk is segmenting sensitive systems and restricting their outbound access, because not every system needs the same level of internet freedom. Sensitive systems include those that store regulated data, hold secrets, manage identity, or control infrastructure, and these systems can often function with a narrow set of outbound dependencies. By placing them in segments with tighter egress policy, you reduce the number of outbound paths available to an attacker who compromises one of those hosts. This also makes monitoring more effective because outbound events from sensitive segments are rarer and therefore more meaningful, which improves signal-to-noise. Segmentation is not merely a network design choice. It is a data protection strategy that makes it harder for sensitive data to traverse uncontrolled routes. When combined with choke points, segmentation creates a defensible perimeter for outbound behavior that is aligned to risk rather than convenience. Operationally, alert tuning is what keeps exfiltration defenses usable, because raw signals from proxies, firewalls, and data loss prevention systems can overwhelm responders if not calibrated. Tuning begins with baselines, where you learn normal outbound destinations, normal volumes, and normal usage patterns for key segments and services, because that context is what turns a spike into a meaningful anomaly. Tuning also involves reducing noisy alerts that reflect routine activity, while keeping coverage on high-risk destinations and high-risk behaviors, such as unusual uploads, new domains, repeated failures followed by success, or sudden changes in outbound volume from sensitive zones. The goal is not to eliminate alerts, but to ensure that when an alert fires, it is actionable and correlates to a meaningful risk story. When alerting is tuned well, responders can move quickly from detection to containment, which is critical because exfiltration often continues until something forces it to stop. A noisy system trains responders to ignore signals, and ignored signals are the enemy of timely response. A memory anchor that captures the control mindset is no data, watch egress, restrict, detect, respond, because it reflects the sequence that keeps defenses practical. No data means you understand what is sensitive, where it lives, and what movement is acceptable, because policy without data awareness becomes either too permissive or too disruptive. Watch egress means you build choke points where outbound traffic can be observed reliably, because visibility must be engineered. Restrict means you shape outbound behavior through egress controls, allow lists, and segmented access so attackers have fewer escape routes. Detect means you apply tools like data loss prevention and behavior monitoring to spot leaks within the constrained space. and respond means you have an operational plan to contain, investigate, and prevent recurrence when a leak is suspected. This anchor keeps you from over-investing in a single layer while neglecting the other layers that make it effective. A useful exercise is to pick 2 choke points in a described network because it trains you to think about where control is realistic rather than where it would be nice to have. In a hybrid network, one natural choke point is the centralized internet egress for on-premises environments, where outbound traffic can be routed through controlled gateways. Another common choke point is the cloud egress path, such as a cloud-native firewall or proxy layer that outbound traffic from cloud subnets must traverse before reaching the internet or external services. The exact choke points depend on architecture, but the exam skill is recognizing that visibility and enforcement must be concentrated where traffic converges. When you can name choke points and explain why traffic should flow through them, you are demonstrating that you understand how to design for monitoring rather than hoping monitoring will appear by accident. This also creates a foundation for consistent policy across environments, which reduces gaps that attackers exploit. To recap, in a way that stays practical, list 3 controls that slow exfiltration, because slowing is often the first and most achievable goal, even when perfect prevention is unrealistic. Tight egress controls that restrict destinations and force outbound through proxies reduce the attacker's choices and increase observability. Segmentation that isolates sensitive systems and limits their outbound dependencies reduces the chance that a single compromise leads to rapid data loss. Data loss prevention policies that detect sensitive patterns and enforce actions at the right channels add a content-aware layer that can block or alert on high-risk movement even when destinations look legitimate. These controls complement each other because one shapes traffic, one reduces exposure, and one adds sensitivity awareness, which is the layered mindset the exam favors. When you can link controls to the paths attackers use, you show you understand both the problem and the practical levers available. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.